Hello guys, in this video we will be talking about 8085 microprocessor pin functions. That is, each of the pin in an 8085 microprocessor has a use. So we will be learning about this and we'll be understanding how it is working and their main functions. So if you are having a notebook, it would be great because it would be easier if we could. It will be easier if you can write it down so you can revise it later. So the signals. So there are six signals altogether. We can classify it into six groups. So uh, the first one is address bus, which is used to carry address. Then we have databus that is used to uh, transport data. Then we have control and status signals that is used to control the various functions, and also status, which is used to check whether something is working or not. Then we have the power supply and frequency signals. Then we have externally or peripherally initiated signals. That is uh, that is for example, you can say the keyboard or the mouse or the monitor. So these are all peripherals. And we have external signal acknowledgement, that is INTA and HLDA. Then we have serial input output ports. So these are the six basic signals, which we can classify all the signals into these six groups. So first of all, let us classify this. This is the 8085 microprocessor. So as you can see here, we have 40 pins from 1 to 40. So the first two are crystal input. Then we have reset out. Then we have serial input and serial output. Then we have interrupts. Interrupts are basically which is used to interrupt the microprocessor. For example, whenever there is some function going on and there is an interruption, so that other function can go on. So all these are done by this interrupts. It is classified into 5. Then we have the address bus, address data bus. So actually it can act in both ways. That is, it can either be a data bus or an address bus. Then we have the VSS, then we have VACC, then we have HLDA, then we have hold, then we have clock out, then we have reset in, then ready, IO, IO input output memory, S1, that is status 1, read. This is a active low signal, that is, if this is true, that means read is not working. Then we have write bar, that is it is reading. Then we have ALE, then we have S0, then we have the address bus from 8A to A15. So this is basically how the multiplexer, the 8085 microprocessor is working. So first of all, let us talk about address bus. So 8085 has 16 address lines that are used as address bus. So these lines are split into two segments, that is A15 to A8 and AD7 to AD0. A15 to A8 are unidirectional, called higher order address, and AD7 to AD0 is used for dual purpose, and it is multi-directional. Okay, so that is the address bus. Then we have multiplexed address or data bus, that is AD7 to AD0 are bidirectional, serve dual purpose. So low order address bus as well as data bus, also known as multiplexing the data bus. Why we are saying multiplexing is that for 0 it will act as an address bus, and for 1 it will act as a uh, data bus. So it is bidirectional. During the earlier part of the cycle, it is used as lower order address bus, that is A7, A0 to A7, and during the later part of the cycle, it is used as a data bus. Lower address bus can be separated by using a latch. Then we have something called address latch enable. As you can see here, we have something called ALE here. So let us. It is the full form. Its full form is address latch enable. It is used to enable the latch address. It indicates whether the bus functions as address bus or data bus. If ALE is equal to 1, the bus functions as address bus, and ALE is equal to 0, then the bus functions as data bus. Then we have the control and status signals. So we have two control signals, read and write. So as you can see here, it is an active low signal. That means if it is active, then that means it is RD bar. So if RD bar is true, that means it is not reading, it is writing. So that is what we call as active low. So in 1 it is low. It is selected input output or memory device is ready to read data, and data is available on the data bus. WR bar, it is active low signal. Data on the data bus are to be returned into selected memory or input output location. Data on the data bus are to be returned into the selected memory or input output location. Then there are 3 status signals, IO, M bar, S1 and S0, to identify the nature of the operation. When high, IO operation; when low, memory operation. Okay. One special signal is ALE. So there is also another meaning for ALE. It is a positive going pulse every time when the 8085 begins an operation. So that is what we understand from that. So S1 and S0 are the status signals similar to IOM bar and can identify various operations. So as you can see here, when S1 is 1 and S0 is 0, then it is a read operation. When S1 is 0 and S0 is 1, then it is a write operation. When S1 and S0 are 1, then it is a fetch operation, and when the S1 and S0 are 0, then it is a halt operation. So these are the status signals which identify what type of operation is going on. So 1 and 1 means fetch, 1 0 means read, 0 1 means write, 0 0 means halt. So this is how it is working. Now let us see a table which completely shows how everything is working from the input output memory, read, write, S1 and S0 status signals. So first of all, let us see from here. S1 and S0 are 1, that means it is a fetch operation. Then if WR bar is 1, that means it is a read operation. So it is an opcode fetch. Then memory read. If it is a read operation, of course the S1 will be 1 and S0 will be 0, and WR bar will be 1 because it is a read operation, and it is 0 because if it is 0, it means it is memory function. Then if it is 1, it means input output. Then we have memory write, where memory will be 0, RD bar will be 1, that means it is write, and S0 will be 1. Then we have IO read, that is IO will be 1, then write bar will be 1, and S1 will be 1 and 0. And IO write, where IO is 1, RD bar is equal to 1, and S0 is 1. Then we have the fourth signal, fourth group, which is the fourth group of signals, which is power supply and clock frequency. So we have VCC, that is the power supply, which is a positive 5 volt. Then we have VSS, which is a ground reference. Then as you can see in the 1 and 2, here we have the crystal input x1 and x2. So what are these? So x1 and x2 is a crystal RCLC network is connected to these two pins. The frequency is internally divided by the two. Therefore, to operate a system at 3 MHz, the crystal should have a frequency of 6 MHz. So therefore, to operate a system at 3 MHz, the crystal should have a frequency of 6 MHz. Then we have the clock output. This signal can be used as a system clock for other devices. What it means is that it is a clock output. So it is being a system clock for other devices. Then we have the externally peripheral initiated signals, that is the reset in, reset out, interrupt, ready and hold. So these are the functions, signals. These have certain uses. So let us learn about each. So from the word reset, what you could understand that from the word reset itself, it is resetting the operation. So reset in means it is resetting the things which are happening inside the microprocessor, and reset out means it is resetting the peripheral which is connected to it. Then we have interrupt, which is used to interrupt the or hold, interrupt the process. So there are 5 types, which are trap, RST 7.5, RST 6.5, RST 5.5, INTR. Then we have ready and hold, which are signals which are ready signal is used to show that it is ready for the next operation, and hold is used to stop the operation for a certain time of time. Okay, so let us understand each in detail. So when the reset pin is activated by an external key, all the internal operations are suspended and the program counter is cleared, that is it is 000H. Then we have the microprocessor interrupt. The microprocessor can be interrupted from the normal execution of instructions and asked to some other instruction called a service routine. The microprocessor resumes its operation after completing the service routine. So that is the use of interrupt. So what it is basically doing is that if you want to execute some other instruction, so we can use interrupt operation. Then we have ready. If the signal at this ready pin is low, the control microprocessor enters into a wait state. Is used primarily to synchronize slow peripheral with microprocessor. Hold. The microprocessor relinquishes control of buses and allows the external peripheral to use them. The hold signal is used in direct memory access. The microprocessor relinquishes the control of buses and allows the external peripheral to use them. Example, the hold signal is used in the direct memory access. So there is also a priority for the interrupts. So as you can see here, trap is going first. That means if there is a happening, the traps, there are two interrupts that is going on. That is the trap and RST 7.5. So the first interrupt which will be going to happen is the trap because it is having the highest priority. So that is what it is basically meaning. Then we have the external signal acknowledgement, INTA bar and HLDA. INTA is interrupt acknowledgement output. The signal is generated by the microprocessor in response to the INTR. When the microprocessor accepts the INTR, it executes an INTA machine cycle. HLDA, hold acknowledgement. On receiving the hold request, the microprocessor completes the current machine cycle and suspends its operation, releases the buses, and sends a hold acknowledgement signal to the TMA controller. So what it is basically saying is that it is a signal. INTA bar is a signal which is used to say that it is ready for an interruption, and HLDA is used to tell the machine that it is now ready for a hold request. Then we have the serial IO ports. So first of all, the SID, which is serial input data line. This line is used in serial communication, and SOD, which is serial output data line. This line is used in serial data communication. So that is all for today's video. I hope you understood what we taught you today, and thank you for watching.